Hello everybody, welcome into another lesson. So today we are going to talk about inverse functions. And again, this may seem like a review from Algebra 2, but it's very important. So in order for a function to have an inverse, it has to be what's called one-to-one. A one-to-one function is where every member of the range has one and only one member of the domain. So there are three ways to determine if a function is one-to-one. The first way we're going to talk about is numerically. So over here to the right, I have a table of numbers. I have some corresponding values in the domain and some in the range. In the domain, again, that's your x value, your input, your independent variable, because you could put in anything for your independent variable and you'll get an output, which is your y value, your range. And it's the dependent variable because it depends on what you put in for your x. So here you have in your domain 0, 1, 2, and 3. This is definitely a function because each member of the domain has only one member of the range. 0 gives you an output of 4, 1 gives you an output of 5, 2 gives you an output of 6, 3 gives you an output of 7. Okay, well, you still have a function, but is it one-to-one? Well, if we remember, when you have in order for a function to have an inverse, or when it becomes an inverse, your domain and range swap places. So you could think of the range as your domain of the inverse function. That's probably the best way to think of it. So if we look at the range, 4 only corresponds to 0, 5 only corresponds to 1, 6 only corresponds to 2, and 7 only corresponds to 3. So this is numerically, this is a one-to-one function. So this function here is in fact one-to-one. Now let's change this up a bit here. Let me change this just a little bit to make this not one-to-one. Alright, so here is a function. Now this time in your domain, 0 goes to 4, 1 goes to 5, 2 goes to 5. It's still a function because each member of the domain has only one member of the range. But if you flip this around, look at your range. 4 only corresponds to 0, but in your range, 5 corresponds to both 1 and 2. So this function would not be one-to-one. So this particular function is not one-to-one in this case. So that's numerically how you would verify. The next method for checking if a function is going to be one-to-one is algebraically. Let's talk about algebraically if a function is one-to-one. So let me throw up a function here. So we have f of x equals x to the fourth. F of x equals x to the fourth. Now algebraically, a function is one-to-one if f of a equals f of b, which would mean that a equals b and only b. If a equals b and only b. So what does that look like? So take in a for your x, put in a to the fourth, set that equal to b to the fourth. Well, you take the fourth root of both sides, you would get a would equal both plus and minus b, simply for the fact that whenever you have an even root, you have to consider both plus and minus the root. If this were an odd root, you'd only consider the even root. You'd only consider the positive root. But whenever you have an even root, whether it's a square root, a fourth root, a sixth root, or so on, you always have to consider both positive and negative of the even root. A equals both plus and minus b in this case, so x to the fourth is not 1 to 1. And I don't know why I have a dash between not and 1. That's not necessary. Alright, what do we got next? F of x equals x squared minus x to the fourth. Alright, so put an a on the left side, so you'll have a squared minus a to the fourth is going to equal b squared minus b to the fourth. So of course we could factor out a common a squared. You would get times the quantity of 1 minus a squared is equal to b squared times 1 minus b squared. Alright, well you would end up then getting 1 minus a squared is equal to b squared times 1 minus b squared all over a squared, which would then give you that negative of a squared equals b squared times 1 minus b squared all over a squared minus 1. So then a squared would equal 1 minus that b squared times 1 minus b squared all over a squared. And then a would have to equal both plus and minus the square root of this whole mess right here of 1 minus b squared times 1 minus b squared all over a squared. So this is definitely not 1 to 1. This is definitely not a 1 to 1 function. In fact, I think you're going to find that pretty much every even power polynomial function is not 1 to 1. It's only going to be 1 to 1 usually if it's an odd power polynomial function. Or you could have a root function that's also 1 to 1. Linear functions are 1 to 1. You'll find that, and it'll make even more sense when we talk about the final method for determining if a function's 1 to 1, which is graphically. Alright. F of x equals 3x plus 4 over 5. F of x equals 3x plus 4 over 5. So we'll take 3a plus 4 over 5, set that equal to 3b plus 4 over 5. Multiply both sides by 5, you get 3a plus 4 equals 3b plus 4. Subtract 4 from both sides, you get 3a equals 3b. And then you get a equals b. Since a equals only b, this is a 1 to 1 function. So this function is 1 to 1 and therefore would have an inverse. F of x equals let's see, yes. F of x equals 3x plus 5. So f of x equals 3x plus 5. So you would take 3a plus 5, set that equal to 3b plus 5, which would give you 3a equals 3b, which means a would equal b. So 3x plus 5 is a one-to-one function, which would mean it would have an inverse. Alright, how about f of x equals 1 over x? F of x equals 1 over x. So this would mean that 1 over a would equal 1 over b. And then you do the cross multiplication for the proportion, you would literally get that a equals b. So yes, 1 over x is 1 to 1. This is in fact a one-to-one function. Now how about this one? F of x equals 4 over x squared. So f of x equals 4 over x squared, so this would be 4 over a squared would equal 4 over b squared. Okay, so you cross multiply, you would get 4a squared would equal 4b squared, which would give you that a squared equals b squared. Now we take the square root of both sides, you would get a equals both plus and minus b, because you got to take the square root of the positive and negative square root of the right side. Since a equals both plus and minus b, this is not one-to-one. This is not a one-to-one function. All right. F of x equals the square root of 2x plus 3. So we've been given f of x equals the square root of 2x plus 3. So algebraically, let's do this. This will be the square root of 2a plus 3 equals the square root of 2b plus 3. Now you just square both sides, you'll get 2a plus 3 equals 2b plus 3, which would give you that 2a equals 2b, which would mean a equals b. So yes, this is a one-to-one function. This function would in fact be one-to-one. Now, here's an interesting one. F of x equals x plus 3 squared, where x is greater than or equal to negative 3. So, if we go to normally algebraically verify that this is one-to-one, you would get that this is not one-to-one, because quadratic functions in and of themselves are not one-to-one. However, you can restrict the domain in such a way that you can have one-to-one function for a piece of this. So let's show you how this works. So x would have to be greater than or equal to negative 3, which means it's going to be everything to the right of negative 3. So it's going to be the right branch of the parabola. So that means we're going to basically take the positive square root. That's what that means. You're going to take the positive square root of both sides in the end. So this would turn into a plus 3 quantity squared would equal b plus 3 quantity squared. And since we're going to the right of the vertex, you're going to take the positive square root of both sides. So you would end up getting a plus 3 equals only b plus 3, which would mean a equals b. Since you've restricted the domain, it would be, in fact, 1-to-1 for just that piece. Now, as a whole, this function's not 1-to-1, but just for that piece, it is. Now, let's say this time here I did x was less than or equal to -3. So now I'm just taking the left branch of the parabola. Alright, so you would still put in a plus 3 squared would equal b plus 3 squared. However, since you're going to the left of the vertex, you're going to take the negative square root of both sides. So you would take the negative square root of a plus 3 squared, set that equal to the negative square root of b plus 3 squared, which would end up giving you the negative of a plus 3 is equal to the negative of b plus 3, which would turn into simply a plus 3 equals b plus 3, which would give you that a equals b. So yes, this would be a 1-to-1 function if you just restrict each half of the parabola, if you restrict each half of the quadratic function. But as a whole, it's not 1-to-1. Alright, so there is the algebraic way. Let's show you the graphic way of verifying 1-to-1 functions. So to verify if a relation's a function graphically, we had the vertical line test. To verify if a function's 1-to-1 graphically, we have what's called the horizontal line test, which also may ring a bell. We take the horizontal line test to determine if a function is 1-to-1. So let's say we're going to do actually the horizontal and vertical line tests. Let's say I have that. Well, first we want to make sure this is even a function. So to determine if it's a function, we apply the vertical line test, and it fails the vertical line test because it intersects the graph at more than one point. So this is not even a function. Therefore, it's definitely not 1-to-1, not a function. All right, now let's say I have a parabola. So first let's apply the vertical line test. And it passes the vertical line test, right? Because it only goes through the graph at one point. So this is a function. Now the million-dollar question is it 1-to-1? This is where you apply the horizontal line test. I'll do that in orange. Doing the horizontal line test, we see it crosses through the graph at more than one point. In order for a function to be 1-to-1, it takes the horizontal line test and it only passes through the graph at one point. If it passes through more than one point, it's not 1-to-1. So this is a function, but it's not 1-to-1. Alright, graph of the classic cube function, f of x equals x to the third. Well, let's do the vertical line test first. It passes the vertical line test. It only goes through the curve at one point, and it would do that for anywhere on the curve. So this is definitely a function. Now the next question is it one-to-one? That's where we apply the horizontal line test. And it's going to cross through the curve at exactly one point, and only one point. So this is a one-to-one function because it passes also the horizontal line test. So there's a one-to-one function. And then, of course, let's see. So we definitely have a rational function here. Well, if we did the vertical line test, it wouldn't pass. So that's probably a bad example. I was just kind of making that one up. Actually, I could do a rational function. Let's just make this better. I had it all shifted. Alright, so here's a rational function. Well, let's apply the vertical line test to see if it's even a function. It might look like they intersect, but they have the asymptote of the y-axis, or x equals 0. So it doesn't matter where I do the vertical line test. It definitely passes the vertical line test. This is a function. Now the big question is this one-to-one? And you may be tempted to say it's not, because it looks like it pretty much becomes a straight line. But it would pass the horizontal line test. The reason being is because it isn't actually staying constant as it looks. It's just getting infinitely closer and closer to y equals 0 without actually reaching it. So this actually is, in fact, a one-to-one function. All right. Now we're going to get into some cool stuff here. So the rest of the time here, we're going to actually find inverse functions. We're going to go on that a function is one-to-one. So let's say we have f of x equals 2x minus 3. F of x equals 2x minus 3. It's linear. It's definitely going to be one-to-one. So we need to find that inverse function. How do you find an inverse function? So f of x is the same as y, isn't it? So y would equal 2x minus 3. Now, to find the inverse of a function, you switch places with the x and y. So that would mean that x equals 2y minus 3. Then you just solve for y. So you would end up getting that 2y equals x plus 3, which would give you that y equals 1/2 times the quantity of x plus 3. And then in final notation, to denote the inverse function, for your y, you would change that into f inverse of x equals 1/2 of x plus 3. So f inverse of x equals 1/2 of x plus 3. So we found the inverse. Now I'm going to show you something cool graphically. So let's just draw the line y equals x. There's a reason I'm doing y equals x. It's very important that I do this too. I want a nice straight line here, as straight as I can get it. Alright. Because graphically, it's very impressive what happens here. So there's y equals x. There's a reason I'm drawing it. F of x equals x. You're going to see why this is called the mother function. Because if you try to find the inverse of f of x equals x, you're going to get f inverse of x also equals x. That's why it's the mother function. It's its own inverse. So let's show you what these look like side by side. I'm going to graph f of x equals 2x minus 3. Let's do it in this green color. So at 0 we have -3. When x equals 1, we have -1 for a value. When x equals 2, we have 1 for a value. X equals 3, we have 3 for a value. X equals 4, we have 5. Alright, so let's see, -1 would be -5. Alright, so in the green is my f of x. This would be f of x equals 2x minus 3. Now, I'm going to graph my inverse in orange. And I'm going to show you graphically what an inverse function looks like. So when x is 0, you get half of 3, which is 1.5. When x is 1, so you get half of 4, which is 2. When x is 2, you get half of 5, which is 2.5. X is 3, you get half of 6, which is 3. X is 4, you get half of 7, which is 3.5. X is 5, you get half of 8, which is 4. Alright, so -1, you get half of 2, which is 1. -2, you get half of 1, which is a half. -3, you get half of 0, which is 0. Okay. So in the orange, I have my f inverse of x. So the cool thing is, f of x and f inverse of x always have symmetry about the line f of x equals x. So graphically, f of x and f inverse of x are symmetric about y equals x. So y equals x is basically the mirror for these. They reflect in the line y equals x. They're symmetric about the line y equals x. So that's a cool graphic tidbit about inverse and regular functions. Alright, there. What's next? F of x equals 3x. Alright, so we have f of x equals 3x. Let's find the inverse of that function. So change your f of x into y to start with. You'll get y equals 3x, which then you'll switch places with x and y. You would get that x equals 3y. Just solve for y, you would get y equals 1/3 x, which in the end is going to end up meaning that f inverse of x is equal to 1/3 x. So now let's graph these side by side. So in the green, I will graph the f of x, which is 3x. You'll still get 0, 0. At 1, you'll get 3. At 2, you'll get 6. -1, you would get -3. -2, you would get -6. I think that's sufficient points. So there's my f of x in green. Now let's graph my f inverse of x in orange. So I still have 0, 0. Now when x is 3, I get a value of 1 for y. When x is 6, I get a y value of 2. When x is -3, I get a y value of -1. When x is -6, I get a y value of -2. So now I have my f inverse of x graphed in orange, and again you can see that symmetry in the line y equals x. All right. I think we get the idea with linear. Let's try some nonlinear functions and show you some stuff here. Good one. F of x equals x to the 5th. All right, so we have f of x equals x to the 5th. Well, let's find the inverse of this. So you're going to make y equal to x to the 5th. Now you just switch places with x and y. You would get x equals y to the 5th, which would then give you that y would equal the 5th root of x. So that means the inverse function, f inverse of x, would be equal to the 5th root of x. So let's start by graphing f of x equals x to the 5th. So 0, 0, you still get that. 1, you still get 1. We're going to graph that in green. But at 2, man, you're all the way up here at 32. 1, you're at -1, you're at 1. 2, you're all the way down to -32. So basically, it's going to look a lot like that for your inverse. It's going to look something like this, almost like a cube root. Now let's graph the fifth root of x in orange. So fifth root of 0 is still 0. Fifth root of 1 is 1. But you'd have to go all the way to the fifth root of 32 to be 2. That's going to be somewhere out here. Let's do that. Fifth root of -1 is -1. Fifth root of 32 is -2. So it's going to look roughly like so. And you see that symmetry in the line y equals x still. Even though these aren't linear functions anymore, they still have that symmetry in the line y equals x. Alright, what's next? F of x equals x to the third plus 1. Alright, so we have been given f of x equals x to the third plus 1. So let's find the inverse of that one. So turn f of x into y. So y equals x to the third plus 1. Now you know what we got to do. We switch places with the x and y. So x would equal y to the third plus 1, which would mean y to the third equals x minus 1. So y would equal the cube root of x minus 1. So therefore your inverse function, f inverse of x, is going to end up being the cube root of x minus 1. Now let's graph these side by side. In green, we will graph f of x, x cubed plus 1. So at 0, you'd have a y coordinate of 1. At 1, you'd have a y coordinate of 2. At 2, you'd have a y coordinate of 9. Now at -1, you'd have a y coordinate of 0. At -2, you'd have a y coordinate of -7. So let's go ahead here. And graph this. So you see there is the original f of x in the green. Now let's do f inverse of x in orange. So when x is 0, you get the cube root of -1, which is definitely -1. When x is 1, you get the cube root of 0, which is 0. When x is 2, you get the cube root of 1, which is 1. When x is 9, you get the cube root of 8, which is 2. When x is -7, you get the cube root of -8, which is -2. All right. So there's roughly what that's going to look like. And you still see that symmetry in the line y equals x. I think it actually looks really cool with the symmetry, if you ask me. So graphically, that's what symmetry looks like between the inverse and the regular function. Now, there is one more piece to this, is verifying that two functions are inverses of each other. There is a way to do that. And graphically, of course, would be to see if there's symmetry between the lines between f of x equals x between them. But I think we've seen enough graphically. Let's just work on verifying that functions are inverses for now. All right. So what we're going to do is verify that f of x and g of x are inverse functions. So here's the thing. If two functions are truly inverses of each other, this goes to composition of functions. So if I decided to take f composition of f inverse of x, I should just get x. Or if I took f inverse composition of f of x, I should also just get x. This time the composition order does not matter. That would mean I should just get x. So when we go to do the composition of these functions, we should just get x to be able to verify that they're inverse functions of each other. If you get anything other than x, they are not inverses. So let's do some examples of that. So let's see. We have that f of x is equal to -7/2 x minus 3, and then we have that g of x equals negative of 2x plus 6 all over 7. I should say the negative of the whole numerator over 7. Now, I should be able to take f composition of g or g composition of f, it doesn't matter, and I should be able to just get x. Let's see if that happens. So let's take f composition g of x. So this would mean f of g of x, which is going to mean f of that negative of the quantity of 2x plus 6 all over 7. And I'm going to put that in for x here in f of x. So let's work that out in a different color. So this would give me -7/2 times the negative of that 2x plus 6 all over 7. All that minus 3, what should that give me? Well, the negatives will cancel each other out because a negative times a negative is a positive. The 7s are gone. So you're literally left with 2x plus 6 over 2 minus 3. Now what does that equal? Well, the numerator, you can divide both terms by 2. You would end up getting x plus 3 minus 3, which would just give you x. You get that magical value of x. And I promise you, if we did it the other way around, g of f of x, you would also get x. But you only have to verify one of the ways. Now, if you just get that value of x, you can say, therefore, g of x equals f inverse of x. That's how you would write it. Therefore, g of x equals f inverse of x, since you get that value of x. If you got anything other than x, even if it were negative x, or x plus 1, or a number, or 0, what have you, it would not be the inverse then. The only way to have an inverse is if the composition of the two functions is x. So, yeah, let's do this one here. F of x equals 2x. F of x, not f of x, I want to do g of x. G of x equals 3x. These are clearly not going to be inverses, and I want to show you why that is. So let's take f of g of x, which f composition g of x, which means f of g of x, which would mean f of 3x. Well, if I put in 3x for in f of x, I would end up getting 2 times 3x, which would give me 6x. And again, that's anything other than x. I got 6x. So g of x does not equal f inverse of x. This is how you would say g of x is not the inverse of x, because you got something other than x. You got 6x when you took the composition. And you would get the exact same thing if you did g composition of f. But let's do a couple more of these. Alright, f of x equals x cubed plus 5. G of x equals the cube root of x minus 5. So we want to show that these two are inverse functions of each other. So we're going to take f composition g of x, which would mean f of g of x, which would mean f of that cube root of x minus 5. So let's go ahead and do that now. F of that cube root of x minus 5. So I'll put in that cube root of x minus 5 for that x. So that'll be the cube root of x minus 5 raised to the third power plus 5. Well, the root cancels out. I just get x minus 5 plus 5, which would just give me x. Well, I got that magical value of x, and only x. Therefore, g of x equals f inverse of x. So therefore, g of x is the inverse of f of x. Let's do one more, and this is going to be a good one. No, actually, let's do two more. F of x equals 1 over x. G of x equals 1 over x. So you're about to learn something very interesting here. F of x equals 1 over x, so does g of x. It also equals 1 over x. So let's take f composition g of x, which would equal, of course, f of g of x, which would equal f of that 1 over x. So now let's go ahead and evaluate that. So put in that 1 over x for the x, you would literally end up getting 1 over x. So you have a complex fraction, you invert the fractions, you would end up getting x over 1, or just x. Therefore, g of x equals f inverse of x. So yes, f of x equals 1 over x is actually its own inverse. Just like f of x equals x is its own inverse. That's kind of a cool tidbit of trivia there for you. Alright, last one this time. F of x equals negative of the square root of x minus 8. G of x equals 8 plus x squared, where x is less than or equal to 0. So this is one of those where the domain is restricted to the left of the vertex of the parabola. That's why you have the negative square root. So let's take then, it might be easier if we do g of f of x. So this time let's do g of f of x. Well, that's going to be the same as g of f of x. And again, order doesn't matter if you want to verify an inverse. If you're just doing the normal composition of functions, order does matter. But to verify if a function's an inverse or not, the order doesn't matter for when you do a composition. So this would be g of the negative square root of x minus 8. So let's go ahead and evaluate that mess. So you would end up putting an 8 plus that negative square root of x minus 8 raised to the second power. Well, a negative squared makes it positive. Squaring a square root makes the root go away. You should just get 8 plus x minus 8, which would just give you x. Therefore, g of x equals f inverse of x. And you could also argue and say, therefore, f of x equals g inverse of x. Either way, they're both inverses of each other. It really doesn't matter however you want to word it. This just proves that they're both inverses. So that's it for this lesson. That's it for this unit. Next lesson, we're going to move into the quadratic, polynomial, and rational functions unit, where in the next lesson we'll talk more in depth about quadratic functions and graphing them. So I hope everyone has a great day. Take care.